Good morning, this is your stats sensei, Mr. Spensei, and I'm going to go over the quiz. The first problem happens to be a confidence interval. So your company sells exercise clothing and equipment on the internet and has more than 5,000 male customers who are runners. That's probably going to be important. You take a simple random sample of 31, so we know N is 31. Male runners who are customers and collect data on their physical characteristics and find their mean weight to be 71.79. So we have this came from the sample, so this makes this our X bar. It's not our population mean. Assume that the population standard deviation is 4.5. Calculate a 97% confidence interval for the mean weight of all such runners and interpret the confidence level. So here we go. Our parameter. Well, what are we interested in? Let mu equal the true population mean weight of the runners who are customers. Because we're not interested in all runners, just the ones that are customers. All right, our conditions, our first condition is random sample. Well, they told us that. And they said it was a random sample of 31. And that was given. The second thing is the N is less than 10%. So N equals 31, which in this case is less than 5,000. Oop, I'm setting that up wrong. So N equals 31. We need to multiply that number by 10. So 31 times 10 equals 310, and that is less than 5,000. So we're good there, less than 10%. Number 3, we need to check for normality. They didn't tell us the distribution was normal, but they did for weights, but they told us our sample size, and 31 is greater than or equal to 30, normal by CLT. Our equation, since it's the confidence interval, is X bar plus or minus Z star standard deviation divided by the square root of N. We're going to list all of our components that go in. And our first component is 4.5, or standard deviation of our population. Our X bar was 31. Our confidence level was 97, or 0.97. And our X bar was 71.79. The next thing asks us to calculate Z star. So we probably need to be drawing a picture. So this area right here is 0.97. And this is my lower, and this is my upper. My mean is 0 because it's a Z-score. So inverse norm, 0.9701, and we're center. So let's get our calculator out and see what that looks like. So second vars, inverse norm, area 0.97, mean is 0, standard deviation of 1. Oops, we're centered. And once again, it's the 0, 1 because we're working with a Z-score. And we end up getting 2.1700, positive and negative. So negative 2.1700 and 2.1700. The one we care about is the positive, because the next thing it's going to do is ask us to plug into that equation. And we plug in and we have 71.79 plus or minus 2.1700. And then we have 71.79 over the square root of 31. So we need to go ahead and run this, and this is going to be we're going to go to stat test. We're going to drop down to number 7, which is Z interval, and make sure stats is highlighted. Our standard deviation for the population was 4.5. The X bar was from the sample mean was 71.79. 31 was our sample size, and our confidence level was 0.97. But we end up getting 70.036 to 73.544. 70.036 to 73.544. So we need to write our conclusion. And in our conclusion, we start off with, we are 97% confident that the true population mean weight of runners who are customers lies within the interval 70.036 to 73.544. All right, so we know our interval came from step 8, but please remember the true population mean weight of runners who are customers comes from number 1, our parameter, exactly the same thing. All right, it also asks us for the meaning. So in other words, we have to interpret the confidence level. And that's the one where it talks about in repeated sampling, which means if we did it over and over again, so in repeated sampling, we expect this method to capture the true population mean weight of runners who are customers how often? 97% of the time. So basically what we're saying is 97% of our time, if we ran it this way, we would capture the true population mean. It'd lie within our interval. 3% of the time, it would not. All right. That takes care of our first one. The next thing we have to do is the hypothesis test. So, number 2, the diameter of a spindle is a small motor is supposed to be 5 millimeters. If the spindle is either too small or too large, the motor will not perform properly. The manufacturer measures the diameter of the random sample of 60 motors from a batch of 900. So, all right, we have a sample size of 60. And we have a population of 900. Whether the mean diameter has moved away from the target size of 5 millimeters. Sounds like this is our claim. So our population mean. The mean diameter of the sample is found to be 4.951. So X bar is 4.951. From past studies known, the population standard deviation is 0.2. And we need a test at an alpha equal to 0.03. This is our level of significance. All right. And they want to see if it is different is our key word. All right, so the very first thing we have to do is we have to write our hypothesis. For our hypothesis happens to be HO mu equals 5 millimeters. That's the claim. HA mu and 5 millimeters. And I just want to say every single time the null will be equal. But in this case, and they'll always have the same numbers. And we never ever use the sample mean. And they said different, which means that is a not equal. All right, our parameter. Let U equal the true population mean spindle diameter. All right, we need to go ahead and set up our conditions. Our first condition is random sample. And it was a random sample of 60. And that was given. 2. N is less than 10%. All right, well, N equals 60. 60 times 10 equals 600. That's less than 900. So we met that criteria. Number 3 is normality. They didn't tell us it was normal, but we can know it's normal by central limit theorem. N equals 60, that's greater than or equal to 30. Normal by CLT, by central limit theorem. Our formula is going to be Z equals X bar minus the mean over the standard deviation divided by the square root of N. That's what we're going to be plugging into. So we need to draw our picture of this. And this is a two-tail, so we're going to be looking for this area in the tail. The claim is that it's 5 millimeters. But we ended up getting a value of 4.951. But remember, it's two tails, so we have to shade both an upper and a lower. So let's go ahead and fill in what we know. Our mean, 5 millimeters. Our X bar, 4.951. N was 60. And we found our standard deviation to be 0.2, or they gave us a standard deviation of the population of 0.20. So we need to plug in. Oh, and so this is a not equal to. So 2 times the probability that Z is less. The reason it's less is because when I plug in, I look and go, oh, 4.951 is, that's supposed to be a minus sign, is less, 4.951 is less than 5. And that's just a minus sign. And our standard deviation is 0.20 divided by the square root of 60. So when I go about this, stat test, Z test, I plug in my data, mean of 5, standard deviation of 0.2, X bar of 4.951, N of 60, sample size of 60, make sure we have the not equal. When we calculate, when we get 0.0577, so our Z equals negative 1.8977. For those of you taking AP, we'd write the probability that Z, or 2 times the probability that Z is less than negative 1.8977. And we end up getting a probability of 0.0577. All right, so our p-value is 0.0577. We need to go back and check out our alpha. We said our alpha earlier was 0.03. So this is greater than, make sure you make them the same length. 577 is definitely bigger than 300. So our decision is to fail to reject. Fail to reject the null. That's our decision. So now we need to write up our conclusion. So our conclusion is simply our p-value is 0.0577. We fail to reject the null. We just stated our decision. We failed to, so there's not enough evidence, so there's not sufficient evidence at alpha equal 0.03 to suggest that, what was our parameter? The true population mean spindle diameter, that the true population mean spindle diameter is, what was our alternative? Different. So is different than 5 millimeters. All right. Thank you for watching. Hope to see you on the next one.